Okay, so we just tentatively concluded that A is not going to enter the basis because it's feasible. C is not going to enter the basis because it's not feasible. But B might be entering the basis. Well, let's think about that. If B enters the basis, it means that the flow on DCW2 has to go back to floating. Right now it's at its upper limit, so it's non-basic. It would have to go back up to floating mode, and which means it has to decrease. Means we're going to decrease the flow on DCW2. That gives us some pause in the algorithm. We have here the network. We have incorporated, so the topic here is modifying algorithm to incorporate upper bounds. We're a little bit hesitant to proceed, and we're wondering whether additional modifications to the algorithm are required. So far, we're using the upper and lower bounds in the finding out which variable in the departing rule. So we had a loop, and which disappeared. We can actually get rid of this loop right now. We don't have that loop anymore. We got rid of it. We increased W2, W1 up to 20, which basically took DCW2 up to its limit of 80. Now it looks like B wants to re-enter the basis, and it means its flow has to decrease, and that's what's giving us pause. So perhaps we also have to modify the entering rule to incorporate upper bounds, and that's what we're looking at right now. So let's whenever we don't know what to do, we introduce variables and give them a name. Let W2DC be the reduction in flow on arc DCW2. If it's going to enter the basis, it means it's going to have to reduce, and which means by some amount. We don't know what that amount should be. So that implies then, therefore, that DCW2 is equal to 80 minus W2DC. Well, if we have that new variable W2DC, what we're going to do is we're going to tinker with this model that we had before. We had a primal and we had the dual, and that's what was driving the algorithm. Now let's replace DCW2 with so this is going to go, and this is going to become 80 minus W2DC. And the same thing here. We're going to have similar change over in the other one. Okay, so this is going to result in plus 800 added to the objective function, and then it's going to change this. Just erase this whole thing. Minus 100 W2DC. That's where we are right now. And then the primal here would also be changed. This sign would change, and this sign would change. We would have minus DCW2 minus W2DC and plus W2DC, and we would have 80 here, we would have minus 80 here, and we would have minus 140 there. Now, Notice that we never incorporated these values here as well as these values here, never made it into the algorithm. This was irrelevant to algorithm. Never use this. So we're going to ignore the fact that these have changed, because that doesn't change anything in the algorithm. But what does change is that now this constraint, DCW2, is we're going to eliminate it. We're going to replace it with a new one, which is that minus W2 DC minus DC plus W2 has to be less than or equal to minus 100. And if we do that, then let's correct this. Let's just get rid of the let's write the equivalent of this. The equivalent of this is that W2 is that DC minus W2 is greater or equal to 100. DC minus W2 is greater or equal to 100, which means that we have a different condition for when flows are at lower bounds than if they're at upper bounds. And this is leading to a whole new rule. So this is the new rules. So this is new entering variable rules. Is that the from minus the to has to be less than or equal to the cost from to if f t is at lower bound, and f minus t has to be greater or equal to the cost of ft if ft is at upper bound. And this now is a modified rule, and therefore, if we go back to where we were, we now can say that this is not incorrect. This is in fact correct, because at upper bounds we have to reduce the flow, and since we reduce the flow for it to become basic, the rule has changed, and therefore this is the optimal solution. There is no infeasibility. So again, going back to the rules, we have to remember that these are in fact the correct entering rules. This was not introduced earlier because all the flows normally start at the lower bounds, but and therefore there was really no opportunity to speak about this. But now that we have it, we now have another algorithm. The next thing that we we have a correct algorithm. The next thing that we want to do is see whether this algorithm can be transposed to be solved entirely on the graph.